Okay, folks, hi. I guess we are live. Let me just check if everything is working all right. Just give me a sec. Let me just check the audio. Okay, folks, hi. Yeah, the audio looks good. Sounds good. Yeah, so since I'm a little early, I'll wait a few more minutes for everyone to join in. Somebody's asking about the forum. We're almost done. Small couple of small hiccups that we're fixing. We'll have that ready, Abhishek. We'll have the forum ready soon. So yeah, we're just working on it. So we'll have that ready, no problem. So somebody's asking about the scholarship test. My suggestion, if you want to prepare for the scholarship test, the best way is to go through the videos that we have. Again, we have publicly posted all the videos for all of the contents for the scholarship test. So you have some concepts from data structures, algorithms, and some concepts from linear algebra, along with practice tests, because we want to give everyone a fair chance at the scholarship test, whether they are already a registered student or they are new student. My best suggestion for you would be to solve as many problems as possible. So most of the questions will be at the same level as the practice test questions. Those of you who have seen the practice tests will easily understand the level at which the problems will be set. And my best suggestion for you is, if you want to prepare more questions than what we have in the practice test, the best choice will be to solve previous year GATE question papers on these topics, right? Because the questions that we will set, again, we have limited our contents. We have just limited ourselves to linear algebra and a few concepts in data structures algorithms, very few concepts actually. And that's by design, because if I have even the whole subject of data structures algorithms, that's a humongous syllabus to cover for anyone in a 15 to 20 day period. So we wanted to see how diligent, this whole test is a measure of diligence. Are you diligent enough to go through the content that we've given, to solve the practice tests, and be well prepared for the exam itself, right? So that's what. Oh yes. So are the videos sufficient for the scholarship test questions? Yes. So all the free videos and the practice tests also. Please also go through the practice tests that are publicly available. Please go through them also, right? So I strongly recommend you check both of these things to get a best idea of what to prepare your best for the scholarship test. Again, we have thousands of students who have actually registered for the scholarship test. So I'm hoping it will be exciting and it will be fairly competitive. So please give your best. Okay, sounds good. So okay, let's wait for a couple of minutes because it's a Sunday evening, so I'm just waiting for everyone. Yeah, Deep. So linear algebra subject test is not available. Okay, I'll ask my team to put that. So yeah, but I believe there are some solved problems, right? I think in linear algebra there are some solved problems which are already there in the course videos itself. I think they'll be sufficient enough, to be honest with you. So that's one. The other thing that I wanted to mention was, so very importantly, so the topics that we were studying, right? I wanted to give you a couple of hints or a couple of tricks that I used when I was a student preparing for GATE. So one of the issues with this whole topic, right, of sets, relations, functions, groups, lattices, posets, this whole concept, right? Because this is the first time we are learning a concept like this, right? Because look at this. Before you learn discrete mathematics in your second year computer science or so, you would have never encountered these abstract algebraic concepts, right? So the first time you go through them, they'll feel very, very abstract, very theoretical. And what is very, very important about them is to understand the concept. And again, there are tons of properties, right? Anti-symmetric, asymmetric. It's so confusing sometimes, to be honest with you. And I was in your same shoes a while ago, right? When 10 years back, or 12 years back, when I was preparing for GATE, I had the same situation. So what I did for all of these algebraic structures, relation sets, what I used to do was, in a single paper, in literally an A4 size paper, or maybe two papers, if I recall, in 2 pages, I would summarize every concept. Okay, I would write everything very concisely. If I have to represent reflexivity, I'll write for all A is related to A. That's what is reflexivity, right? So I would write all the properties of all the concepts that we learned in one paper, and I try to revise it. So literally I think it was 2 papers, not one paper, because I couldn't fit everything in one page, if I recall. So I literally used to have an A4 size sheet, 2 sides, all of the concepts, all of the important properties. Again, the properties are extremely important to solve problems in gate. Like, for example, the order of an element divides the order of a group. Very, very important property. So what happens is most of the questions in gate are not like deep proofs, right? Because proving many of the statements in group theory or with lattices takes time. So what gate is mostly testing is, do you know the most important theorems in group theory with respect to lattices, posets, relations, and functions? And you just have to apply these theorems, right? So that's a very, very important thing. So mostly, again, I'm not saying always, but most of the, if you look at most of the gate questions, they're often you just need to apply the theorems that we have learned as part of the course videos. That's why I've taken a lot of time and extensively I've spent a lot of time going through the course, going through most of the theorems. Again, just in the interest of time, I couldn't prove every theorem, because if I started proving every theorem with respect to lattices, groups, cyclic groups, abelian groups, right, that would be like a 40 hours course just itself, right? So in the interest of time, I didn't go and prove everything. In some instances, I just stated them, right? Of course, there were some instances where I went ahead and proved some of the important theorems, right, intuitively. So sounds good. So let's get started now. We have 25 questions ahead of us. So with those couple of hints, my suggestion here is let's get started. We have 25 questions. We'll try to solve as many as we can. I believe Naveen and rest of the team are also online. They're trying to answer as many questions about scholarship test as possible. Okay, so let's get going. Let's go through the questions now. Again, to be honest with you, of the 25 or so questions that we have, 3 or 4 of them are hard, to be honest with you. So 3 or 4 of them are slightly above the gate level. I struggle to solve them. I'll tell you which problems also. Okay, but most of the other problems, like 21 problems or so, 21, 22 problems are straightforward, easy. Or they're actually at gate level, actually in gate, right? In the gate exam, from all of these algebraic structures, sets, lattices, all of these things, questions are often very easy. It's a very, very scoring subject if you can understand these concepts and be able to apply the properties of these methods. It's very, very scoring subject. Once in a blue moon, you might get a hard question, right? So let me just share the screen with you. Okay, so I'm sharing the screen. So let me go ahead. Okay, so let's start solving these problems. Let me hide this. I hope everything is visible. Yeah, so this is visible. Very good. So let's look at this problem. This is a straightforward problem. So calculate the size of power set of A if A is an empty set. Look at this. It says A is an empty set, right? Which means how many elements are there? 0 elements are there, right? Which means if A is an empty set, what is the size of A? What is the size of A? Size of A equals to 0, right? Then what is the size of the power set of A? The size of power set of A is 2 power the size of A, right? Is 2 power the cardinality of A, or the size of A, which is 2 power 0, which is equal to 1. Right? So it says power set of A. Okay, so what about power set of A? What is the size of this set? The size of this set is 2 power the size of this set. Right? What is the size of this set? 1. So the size of this is 2. Right? So the size of power set of A is equal to 2. Again, very simple concept here. Right? Very, very simple concept. And again, this is typically your 1 mark questions. You can solve this in like 20-30 seconds. Okay, extremely simple problem. So let's go to the next one. Okay, this is a more interesting one. This is actually fun. So this is again not a hard problem, but this is an interesting problem. Okay, again, actually for our students, this should be a trivial problem, right? Because we have studied the concept of inclusion exclusion, right? So if you recall, we have studied inclusion, the principle of inclusion exclusion for counting. We have seen this for 2 sets. We have seen this for 2 sets. We have seen this for okay. Okay, so where are we? Yeah, so okay, so for this question, right? So what do we need? Okay, so we have seen the principle of inclusion exclusion for 2 elements, for 3 elements, also for n elements, right? So if you notice, we have also seen this. Again, we introduced this concept, I think, when we had to count the number of into functions, right? We introduced this concept when we had to count the number of into functions as part of our course videos, right? So this problem is straightforward. This problem is very simple, right? So what does it say? It says, okay, which of the following sequence of set operations counts the number of elements that are exactly in one of A, B, or C? right? So answer is straightforward B. You just apply inclusion, exclusion. It's literally staring at you. It's a very, very simple, straightforward question, right? So let's go to the next question here. Again, some of these easier questions, again, this is a harder one. Okay, so this, I wouldn't say hard. This is actually a tricky one. I'll spend more time on this question, right? The previous two are actually fairly straightforward. This question is actually a lot of fun. Okay, so it says I have 100 students. Okay, so let's say this set U consists of all the students, and let's say this, so the size of U equals to 100, who took a quiz with 3 problems. There are 3 problems: easy, medium, and hard. 52 people solved easy. Okay, so let's call all the people who solved easy as E. Okay, so this is 52. Okay, 35 students solved medium. So 35 students solved medium. Very good. And 32 students solved hard. Okay, so 32 students solved hard. Now, also 37 students solved exactly 2 out of the 3 problems. So 2 out of 3. Exactly 2 out of 3 problems have been solved with 37 students. And okay, 2 out of 3 problems, and 10 students solved all the 3 problems. So 10 students solved E, M, and H, right? So this is 10. Now it says how many students solved none of the 3 problems. It's a very good question. Okay, so let me draw and explain you. Okay, so that this concept is, let's assume I have 3 sets here. Okay, again, you can't use the simple principle of exclusion and inclusion here, because you don't have, so it says 2 out of 3 are here. Okay, let's actually work it out. Okay, carefully. Again, this is a slightly tricky problem, not a hard problem. You have to be careful. Many people I've seen just simply apply the principle of inclusion and exclusion and mess it up. Okay, so what do I want? I want number of students who have solved none of the 3 problems. So first, let me try to find the number of students who have solved at least one problem. Okay, so which is this set, right? Which is the size of this set, right? If I find the number of students who have solved at least one problem, if I subtract this number from 100, I get the number of students who have solved none of the problems, right? Let's look at this. So what do I have? I have 100 students in total. What is the size of E? Okay, so let's, instead of saying A, B, C, let me call them E, M, and H. Okay, so now let's see. What if I do size of set E plus size of set M plus size of set H? Okay, so look at this. I'm counting all the elements here. I'm counting all the elements here, and I'm counting all the elements here. Now let's see what is happening. Let's look at these. What are these elements? What are these red shaded elements? Okay, and I'll also shade this in blue. Okay, what is this blue elements? This blue elements is the set of students who have solved all the 3 problems, and we know the set of students who have solved all the 3 problems is 10. Right? What about this red region? This red region. Look at this. This red region is only this part, and this part, right? So this red region is a set of students. So this red region is a set of students who have solved E and M. This red region is a set of students who have solved E and H. This red region is students who have solved M and H. So if you take the union of these 3 red regions, if you take all these 3 red regions together, that's the number of students who have solved 2 out of 3 problems. So that the whole red region is 37, right? This is important, right? So what is given? The number of students who have solved 2 out of 3 problems is 37, which means the number of students in these red regions, right? Because these students have solved 2 out of 3 problems, right? That's what is 37. Now what do we have to find? Number of students who have solved at least one problem. Okay, so let's look at this. So when I'm doing E plus M plus H, okay, so when I'm doing E, which means I'm taking all the elements here, I'm taking all the elements here, I'm taking all the elements here. When I'm doing this red region, let's start with this. Okay, let me color it in a different color. Okay, so let's take this region. Okay, this region is counted twice. This red region is counted when I'm counting all the elements in E, also all the elements in M. So this region is counted twice. Similarly, this region is counted twice in these 3 numbers. When I sum up these 3 numbers, this region is counted twice, this region is counted twice, and this region is also counted twice. Which means I have to subtract all these 3 regions once, right, to get the appropriate number, which means I'll subtract minus 37. Okay, what is E? E is 52. E is 52. What is M? 35. What is H? H is 32, right? Because these 3 regions are counted. Remember, these 3 regions are counted twice. So if you subtract once, they'll only be counted once. Very good. What about this blue region now? Okay, so now comes the interesting part. What about this blue region now? This region. Okay, so let me not change the color here. What about this blue region? This blue region was counted 3 times. It was counted in E, it was counted in M, it was also counted in H. Right? It got counted 3 times. So let me write that here. It got counted 3 times. Right? It got counted 3 times, which means I have to subtract 2 times of this. And I know the size of this set. I know the size of this blue set is 10. Right? Which means I have to subtract 2 times that. I have to subtract 2 times that to compensate for it. Now every region, this region is counted once, this region is counted once, this region is counted once. This is counted once now because I've subtracted it once. This region is counted once, this region is counted once, and this region is also counted once because I've subtracted 2 times of this. Now, if you simplify this whole thing, you'll get 62. Right? You'll get 62 here. Right? Now this is basically the number of students. So what am I getting here? What is this? What is 62? 62 is the number of students who have solved at least one problem. Because these students would have solved only one problem. These students would have solved 2 problems. These students would have solved 3 problems. Right? So number of students who have solved at least one problem is 62, which means number of people who have not solved any problem is 100 minus 62, which is 38. Right? Again, this problem is very interesting because to solve this problem, you cannot use inclusion exclusion. Many people make that mistake and start using this as the inclusion exclusion part, right? The intersection of 2 sets. No, you have to be very careful when you read the question. So that's one of the common mistakes done here. And to solve this problem, you have to understand how the principle of inclusion exclusion came into existence. That's why I like this question. Okay. See, if you know how to arrive at the principle of inclusion exclusion for 3 sets, you can solve this if you read the question carefully. Very, very interesting question. That's why I like this problem. This is not a hard problem. This is a tricky problem where many people make a mistake, right? So I hope this is a good one actually. So the next one. Okay, so let's go to the 4th question now. Okay, so the 4th question says, consider the following statements. A relation can be both symmetric and anti-symmetric. Again, whenever I see statements like this, because I don't have a very good memory, I tend to forget. What is symmetric means? Symmetric means if A is related to B, then B is related to A. I just remember it symbolically. What does anti-symmetric mean? It's not asymmetric. Remember, it's anti-symmetric. Okay, anti-symmetric means if A is related to B and B is related to A, then A is equal to B. That's what it says. Asymmetry is different. Asymmetry says if A is related to B, then B is not related to A. Okay, can a relation be both symmetric and anti-symmetric? They're not opposites of each other if you think about it. If you think about it, they're not opposites of each other, right? Imagine if I have a relation. Imagine if I have a relation which consists of, which is an identity. Let's take the identity relation, right? This is an identity relation. 1 maps to 1 and 2 maps to 2, right? So this is an identity relation. Now look at this. Now this is both symmetric. This is symmetric, right? Because A related to B and B is related to A. And if A is related to B and B is related to A is related to B. Sorry, A equals to B, I'm sorry. Okay, so if you look at this identity relation, it is both symmetric and anti-symmetric. Okay, I'm not talking asymmetric, I'm talking anti-symmetric, right? So a relation can be both, like this identity relation, right? Next, the question here is, there exists a relation which is both reflexive and irreflexive. Actually, if you recall, when we learned reflexive and irreflexive relation, there is a very interesting thing that is said. What is the smallest reflexive relation? Null set. What is the smallest irreflexive set? Null set also. Both of them are, so a null set is both reflexive and irreflexive, which means there exists a relation which is both reflexive and irreflexive, which is a null relation, right? So actually both of them are true. Again, if you have gone through the course videos, this is fairly straightforward because we discussed this very, very clearly. Okay, I think I also mentioned this in the course videos, that phi is the smallest reflexive. Again, I remember working this out, right? That phi or the null set is a reflexive relation, and null set is also a reflexive relation, right? So it's very straightforward question. If you're careful and if you could construct a simple example, this problem is straightforward, right? So now let's look at another question. Okay, this question again is not hard. It is slightly tricky. Okay, so let me solve this question, right? So what does it say? It says, imagine if I have a function from real numbers to real numbers such that f of x is x square minus x plus 1. Then what is f of 0? Okay, let's try to work it out, right? So let's assume y equals to f of x, just for simplicity. Okay, okay. Then can I write what can I write f of y as? What is f of y? F of y is y square minus y plus 1 from this. Let's assume, because there's a function from real numbers to real numbers. This is also a real number, right? This is also a real number. Hence, I can apply this, right? So what does this imply? This implies f of x, right? That's what this means. I'm repeatedly applying it. This is equal to f of x squared minus f of x squared, not here, but squared, f of x squared, right? The whole f of x ka square minus f of x plus 1, right? Yeah, so that makes sense, right? This is y squared, right? Y squared is f of x squared. Okay, so now let's see. So f of y, okay, so I got this, fair enough. Okay, now let's see. If I put x equals to 0, what happens? Okay, if I say x equals to 0, right? Now, if I say x equals to 0, what happens now? Or can I also say, okay, so let me also write another statement, right? So we got, okay, so let me go step by step more carefully. So f of x is this, right? And what is f of x? F of x is x square. So what is f of x? So what is f of x? Okay, sorry. So what is f of x? F of x is x squared minus x plus 1. So can I write this way? Can I write this as minus fx plus 1? Right? Look at this. I'm just replacing this with this formula. Okay, now we got something, right? Now if I put x equals to 0, now if I place x equals to 0, then what happens here? Then this will say f of 1 equals to 0, 0, right? F of 1, so this is equals to f of 0 squared. This is equal to f of 0 squared minus f of 0 plus 1, right? So, okay, so if x equals to 0, yes, so f of 1 equals to this, right? Now if I place if I say x equals to 1, then what happens? Then I get f of 1 square minus 1 is 0 plus 1. So I get f of 1 also equals to f of 1 squared minus f of 1 plus 1. Right? Look at this. Look at this. Okay. So now look at this. Now what do I have? I have f of 1. So this, if I equate both sides, look at this. I have f of 1 equals to this, and I have f of 1 also equals to this. Right? Now let's see. Now what is f of okay, let me treat what we want, f of 0, right? I'm trying to get to that. I'm trying to get to f of 0. So I have f of 0 here, and I'm trying to figure out what is f of 0. So can I say, so what do I have here? If x equals to 0, I have f of 1 equals to, okay, so this is getting slightly tricky, but let's figure out. See, I try to get into this form because I want f of 0. Okay. So if I put x equals to 0, then f of 1 is f of 0 squared minus f of 0 plus 1. Okay, perfect. If I place x equals to 1, this is what I get, right? Now, what if I say, okay, so let's actually equate both these sides. If I equate both of them, what do I get? If I equate both of these, what do I get? Okay, so I get these two will cancel out, right? That will not help us much actually. So f of 1 squared. Okay, so f of 1 squared. Okay, let's try to equate both sides, right? If I equate both sides, this is not helping me. Okay, so okay, or else let's simplify this. Okay, this is better. Let me simplify this. Okay, that's a better strategy actually. Let me simplify this, because look at this. Everything is in the form of f of 1, so I can compute f of 1 from this actually. Okay, that's the idea there. So what can I rewrite this as? I can rewrite this as f of 1 square minus 2f of 1 plus 1 equals to 0, right? This is a quadratic equation, right? This is a quadratic equation if you think about it, right? This is nothing but f of 1 minus 1 squared equals to 0. Okay, so this is a good idea, because here I have a quadratic equation f of 1, right? So what does this imply? This implies f of 1 equals to 1. Very good. So if f of 1 equals to 1, look at this. Now I can solve this also. Good idea. Yes. So f of 1 equals to 1, right? Which means f of 0 squared minus f of 0 plus 1 equals to 1, because this is equal to f of 1, right? So 1 gets cancelled. I have f of 0 multiplied by f of 0 minus 1 equals to 0. This is what I have. Now, can f of 0, so I have two options. F of 0 can be 0 or f of 0 can be 1, right? Now, the problem here is if f of 0 is 0, look at this. Let's assume f of 0 equals to 0, right? Then f of 0, what will f of 0 be? F of 0 will be equal to 0, right? F of 0 will be equal to 0, right? If you think about it. But what is, so, but if you use this formula, f of 0 will be equal to 1. right? If you use this formula, this will be equal to 1, which means f of 0 cannot be equal to 0. The only valid option is f of 0 equals to 1. This is the only valid option, right? Again, this is the tricky part here for me was to actually recognize that this is a quadratic equation, solve it, whatever output we got, we repurpose it because we can use it here. And this is also a quadratic equation. Now I'll try to solve it. Okay, slightly tricky. I think I got a little lost here, right? But otherwise, it's a straightforward problem, right? So this is again a good question. So the next one is, this was a hard one. I actually struggled with this question, to be honest with you. So this question was hard. Okay, I literally struggled. So it says, let's assume I have a function f of x and a and b are positive integers. Again, this function is defined on positive integers, right? If a is greater than b, then fa is greater than f of b. So this is called monotonicity, right? Monotonicity, right? We have discussed about monotonicity when we learned calculus. Now it says we are also given this. Remember, it's a function on positive integers. It follows monotonicity, and it is given this. Now the question is, what is f of 11? Okay, so this is slightly tricky. So let's go step by step. Actually, frankly speaking, I took like 10 to 12 minutes to actually solve this problem, to be honest with you. I got stuck a couple of times, right? So, okay, so we are given that so let's assume y equals to f of x. Let's assume y equals to f of x, right? Then, can I write f of y? So I'll write f of y as y square plus 2, right? Obviously, because look at this. This is a function from positive integers to positive integers. So this makes sense, right? f of y is y square plus 2, right? So what is f of y? What is y, right? So f of y is y square plus 2. Also, we have what is f of y, right? What is f of y? F of y is f of x, right? F of y is nothing but f of x, because y is nothing but f of x, right? Which is equal to x square plus 2, which is equal to x square plus 2, right? So f of y equals to this. So if I can write this whole thing, look at this. So I can write this as so I can rewrite this as, instead of f of y, I can write it as x square plus 1. So x square plus 2. I can write it as f of x square plus 2. This part I'm replacing here is y square. What is y square? What is y? F of x is f of x squared plus 2. Okay, very good. So till here, everything is good. Now, if I place x equals to 1, let's assume. So if I place x equals to 1 in 1, okay. So if I place x equals to 1 in this, okay. So what is f of 1? F of 1 is 1 square plus 2, which is equal to 3, right? So I got this. Okay, if x equals to 1, so let me just write it here because I'll use this again, right? If x equals to 1, I have this fact. Okay, so let's keep going now. Okay, again, there are a lot of leaps that I had to make while solving this problem, right? So now we have f of 1 equals to 3. Very good. Now let's take cases. Let's assume f of 1 equals to 1, because look at this. It's a function from positive integers to positive integers. If f of 1 equals to 1, what happens then, right? If f of 1 equals to 1, then obviously f of 1, because f of 1 equals to 1 and f of 1 equals to 1. So this will be equal to 1, which is not true, right? Because given this formula, f of 1 is actually 3, which is not equal to 3. So this cannot be equal to 1. Okay, so this cannot be equal to 1. Next option. Okay, can it be equal to, so let's see, can it be equal to 2? Before we go and see whether it's equal to 2, I also want to prove that it cannot be. So let's assume, so the other option is, let's say 3. Let's take 3, right, for example. Okay, so what is f of 3? What is f of 3? F of 3 is, look at this. What is f of 3? F of 3 is, okay, what will f of 3 be? Okay, f of 1 is equal to 3, right? Okay, so I have this. So f of 1, look at this, f of 1. Okay, let's take another example, right? Let's take another example. Okay, sorry. So let's assume. So we assumed here that f of 1 is equal to 1 and we failed. Now, if f of 1, let's assume f of 1 equals to 3, then what happens? Let's see. If f of 1 equals to 3, right, then what happens now? Will something break down? If f of 1 equals to 3, then I need to get f of 3 equals to, right? If f of 1 equals to 3, because I want to find f of 1 first, because if I find f of 1, I can start solving this problem carefully, right? See, if I find f of 1, I can find f of 3. If I find f of 3, I can find f of 11, because 11 is nothing but 3 square plus 2, right? That's why I'm struggling to find what is f of 1, right? So let f of 1, if f of 1 equals to 3, right, then what happens? Then f of 1, okay, so then we also know f of 1 equals to 3, right? So which means I'll get f of 3 equals to 3, right? But look at this. But I already know from this formula, what do I get? From this formula, what do I get? From this formula, right? So from this formula, I know that f of 3 will be, so this is what? 1 square plus 2. Look at this. From this formula, I also have this formula which I'll use, right? So if f of 1 equals to 3, if f of 1 equals to 3, it says f of 3 equals to 3. This is the result that I'll get, obviously, right? If f, because this is true, because this is true, I'll get this result. But here is a problem. Look at this. If x equals to 1 here, what happens? This becomes f of 3. See, from this equation, I'll get f of 3 as f of 1 squared. I'll get f of 1 squared plus 2. I assume that f of 1 equals to 3. So this becomes 11, which is not equal to 3, which means f of 1 cannot be equal to 3 also, right? See, f of 1 cannot be equal to 1. It cannot be equal to 3. Okay, so two problems. Okay, so the next problem here is, I'll also prove that f of 1. So let's assume f of 1 is greater than 3. Let's assume. So just for simplicity, let's assume it is equal to 4, which is greater than 3. Okay. So I can prove that for every value greater than 3, f of 1, actually, I'll prove that f of 1 cannot be greater than 3. Okay, see, what are all the positive integers we have? We have 1, 2, 3, 4, so on. We proved that f of 1 cannot be equal to 1, right? We proved that it cannot be equal to 3. If I prove that it cannot be equal to greater than 3, then I'm left with only one option, that f of 1 equals to 2, right? Because it's a function from positive integers to positive integers, right? So now let's see how to prove this. Again, till now, if you notice, we have not used this. We have not yet used this till now. So let's try to use this. So the way I'll use this is this. Okay. So let's assume, just for simplicity, I can use this for any value greater than 3. So let f of 1 be equals to 4. Let it be. Then what is f of 1? What is f of 1? Which is equal to f of 4, which is equal to 3. Okay. Now, what does this say? This says that if a is greater than b, look at this, 4 is greater than 1. If this is true, then f of 4 should be strictly greater than f of 1. Now, what do I have? I assume that f of 1 equals to 4. I got f of 3 equals to 3. This is not true, because it is not satisfying. Because if I assume any value, look at this, if I can take 4 here, I can take 5 here, I can take 6, any value greater than 3. If I take any value greater than 3, this monotonicity will be broken, right? Hence, it cannot be any value greater than 3, which means what will we end up with? We'll end up with the only one option, which is f of 1 equals to 2. Now, if f of 1 equals to 2, now I can solve this problem straightforward, right? If f of 1 equals to 2, then this is straightforward. Then what is f of 3? I place x equals to 1, right? If x equals to 1, this becomes 3. Then f of 3 equals to f of 1 squared, right? What is f of 1? 2, right? 2 squared plus 2. So this is equal to 6. Now, what is f of, so if I put x equals to 3, so 3 square plus 2, so I'll get f of 11. What is f of 11 now? F of 11 is f of x square, which is f of 3 square, which is 36, plus 2, which will give me 38, right? So the answer for this is 38. Okay, so the trick here that I realized was, because again, this is a very important thing. It's a set of positive integers. Okay, it's a set of positive integers, which means f of 1 can either be 1, 2, 3, as I told you, right? Can only be 1, 2, 3, 4, 5. It was easy to prove that it's not equal to 1. It was slightly tricky to prove that it's not equal to 3, 4, etc. Right? The only easy part was once you remove everything else, you'll realize that f of 1 equals to 2. And once you get that, the whole problem is simple. Okay, this is a slightly tricky problem. And to be honest with you, this is one of the harder problems in this test. And I think this is certainly slightly above the gate level. Okay, certainly this is hard even by gate standards. This is a hard problem, but it's a fun problem. Again, it's not easy. I mean, truth be told, even if I practice, I don't think I can solve it in 2 to 3 minutes. It took me a while to figure out this whole solution. Okay, sounds good. So, okay, so let's go to the next question now. There are some slightly harder questions here. Okay, so let's look at this. Okay, so what does it say? Consider the following statements. So in a lattice L, if each element has at most one complement, okay, so we know what a complement is, right? An element A and the complement of A, right? If I take the OR of both of them, I should get 1. An element A and the complement of it should get 0. If you've forgotten what a complement is, right? Then L is a distributive lattice. Okay, so let's see if this is true. So we know what is not a distributive lattice, right? If you remember, we discussed in the course videos that a kite is not a distributive lattice. Okay, so for the kite, look at this kite lattice, right? This is not it's a lattice but not a distributive lattice, because I think one of the properties that we discussed was if you have kite lattice as a sublattice of any lattice, it is not a distributive lattice, right? It's a very important property. So again, kite lattice helps us a lot for many of these problems around distributive, because kite is not distributive, right? So kite lattice is not distributive. Okay, so it is not a distributive lattice. Very good, right? But each element has at most one complement. Yes, each element here has a, so okay, this element has this complement, this element has this complement. Okay, so okay, so if you look at this, right? So every element, or let me make it slightly more complex, right? Instead of just using a kite lattice, let me just make it slightly more tricky. What if I have a lattice like this? What if I have a sublattice as a kite lattice now? Okay, let's see this. Okay, if I have this, every element has at most one complement, right? Every element has at most one complement. Yes. So in this, every element has only one complement, and it's not a distributive lattice because kite lattice is a subset of this, right? Simple. So 1 is not true. So 1 is actually false. What about 2? Let's look at 2, right? So for 2, a sublattice of a complemented lattice is complemented. We know that this is a complemented lattice. We know that this is a complemented lattice. Obviously, for every element, there exists a complement. And of course, this is your 1 and this is your 0. But if you take a sublattice here, look at this sublattice. Look at this sublattice, right? This chain of 3 elements is a sublattice of this lattice, but this is not complemented. What is the complement of this? There is no complement of this, right? So this chain is not complemented, right? So while this is a complemented lattice, its sublattice is not complemented, so this is also false. So what will we end up with? We'll end up with option D. Both options are false. Okay, sounds good. So now let's go to question 8. Again, some of these are tricky, but they're fairly doable. Now, what does it say? It says, let P be a relation on R comma R defined as pairs A comma B such that A square plus B square equals to 1. Then which of the following is true? Okay, so we have something called as a reflexive relation. Again, for those of you who have forgotten what is we have something called an equivalence relation. What is equivalence? Equivalence is something that is reflexive, symmetric, and transitive. Right? That's important, right? So again, both of these actually mean the same thing, right? Because a lattice has to be a partial order to start with, right? Because not exactly same, because a lattice is a partial order which has wherein you can have LUB. So lattice is basically LUB plus GLB plus partial order plus posset, right? That's what a lattice is. Now let's look at this actually. So it says A and B are real numbers such that A square plus B square equals to 1. So let's assume 0, 1. Okay, this set 0, 1, or sorry, this ordered pair, sorry. So this ordered pair 0, 1, look at this. This ordered pair 0, 1 will belong to this relation, obviously, because 0 square plus 1 square equals to 1. Similarly, 1 comma 0 will also belong to this relation because 1 square plus 0 square equals to 1. Very good. But what does transitivity say? Transitivity says if 0 comma 1 and 1 comma 0 exist, then 0 comma 0 also should exist. But 0 comma 0 cannot exist in this set because 0 square plus 0 square is not equal to 1, which means this relation does not satisfy transitivity. Right? Remember, it doesn't satisfy transitivity. Because it doesn't satisfy transitivity, it's not an equivalence relation. Now, before we go to lattice, let's look at partial order relation. What is a partial order relation? A partial order relation has to be reflexive, anti-symmetric, right? It has to satisfy anti-symmetricity, but also transitivity. We just saw that this relation does not satisfy transitivity, which means it's not even a partial order. If it's not a partial order, it cannot be a lattice, right? Because a lattice is basically a poset with both LUB and GLB, right? So it's not a lattice. So none of the above is the right answer here. So transitivity is the key, and coming up with this example was the key in solving this problem. But it was actually fairly straightforward to come up with this. Okay. So now let's look at question 9. Okay. So consider the following Hess diagrams. So we have these 4 Hess diagrams. Which of the above represent a lattice? And what is a lattice? Lattice is a poset. Look at this. The way I remember is a lattice is a poset where the LUB and GLB exist for every pair of elements. That's what it is. Okay. This is my definition. This is how I concisely remember definitions of any algebraic structures. Okay. So to be honest with you, again, this is my own personal data point here. So this whole concept, I've used sets extensively in my own work experience. I've also used relations as part of databases. I've used functions certainly, but I've not used posets. To be honest with you, I've not used posets. I've not used lattices much. Also, I've not used groups, right? I've not used some of these algebraic structures much in my own career. That's probably because actually groups are used by the crypto guys, right? People who study cryptography, network security, etc. Because I mostly worked on machine learning and AI, right? Of course, I also worked on big data. I also worked on some pieces of software engineering, etc. But I never worked in cryptography per se. And hence, I've not actually used, to be honest with you, I've not actually used some of these concepts day to day. So before I started preparing for this GATE course and preparing all the notes and everything, I actually forgot most of these concepts, to be honest with you. I actually forgot most of these concepts because I've never used many of these concepts in my own career because I didn't work in cryptography and network security, right? So that's why that's why when I was making notes, I actually wrote the notes as if I'm a student preparing for GATE, to be honest with you. I think this is one of the rare subjects in computer science which I personally did not apply much in my career over the last decade. I think every other concept you take, even Turing machines is something that I've used in my career. So I've used a lot of concepts from compilers, obviously, because we wrote some very efficient code when I was working. So I've used almost every concept that I can recall, except these concepts, because I did not work in cryptography. That's why I'm slightly slow when thinking about solving these problems, right? But again, that's my personal data point. I wish I got some exposure to working in cryptography also, so that I would have had a better appreciation of some of these algebraic structures. Okay, so coming back to this question here. Which of the following is a Hess diagram, right? So let's see. So, sorry, which of them is a Hess diagram of a lattice? Okay, so that's the question, right? So this is a lattice, we know. This is a diamond lattice, okay? So I think there is a small problem with this. Okay, so because if there is no dot here, right? If there is no dot here, look at this. If there is no dot here, if there is no dot, then this is exactly same as the diamond, right? Because this is a transitive relation that I can come with this. So I'm assuming that there is a dot. So this is a kite. Kite is a lattice. So this is a lattice. This is a lattice. Okay. So 1 and 4 are surely lattices. So this cannot be right. This cannot be right. So either A or D. Now the question here is 3 a lattice? Look at this. Is 3 a lattice? It's a very good question, right? So again, we have seen this example in the course videos. We've seen this example, right? So if you take these two, okay, what is the upper bound? This is an upper bound. This is an upper bound, and this is an upper bound. Right? All these three elements are part of the upper bound of these two elements, right? Now, what is the lowest upper bound? What is the lowest upper bound? Now, I can't even compare these two elements. So I can't have a lowest upper bound, which means for these two elements, I don't have a lowest upper bound, which means it's not a lattice. Because for a lattice, for every pair, I need to have a lowest upper bound and a greatest lower bound, right? So hence 3 is not a lattice. So the answer A is the right answer here, because 3 is not a lattice. Okay. It's a very good question. Okay, again, we have already seen this in our course videos. I've actually taken exactly this example as part of the course videos examples, right? So now let's look at another question. Okay, so which of the following is not a distributive lattice? Okay, so let's see so we know what is a distributive lattice, right? A lattice which satisfies the distributive property. Okay, so let's go one by one, right? So, okay, so this is basically the power set of 5 elements and subset, right? So with this relation, with the subset relation on a power set, what is your LUB? Your LUB, least upper bound, again, we discussed in the course videos, is same as the union, right? And your GLB is same as the intersection. Your GLB is nothing but the intersection, right? Again, for this relation of subset on a power set of elements, right? On a set of power set, on a power set, right? Your LUB and GLB are union and intersection. We know that set union and set intersection are distributive in nature, right? So this is certainly a distributive lattice. So the question is, which of them is not a distributive lattice? This is obviously a distributive lattice. Okay. So let's look at option B. What is this option B now? So option B here is D27 and divided by, or divides. So D27 is the divisors of, so this is the divisors of 27. What are the divisors of 27? 1, 3, 9, and 27. These are the divisors. And the relation here is divides, right? If I actually draw this, what do I get? So if you notice this, I get a chain 1, 3, 9, and 27. A chain is a tosset, and we know tosset is distributive, right? So this is also distributive. Now let's look at the third one, which is a set of real numbers and less than. So how does the Hess diagram for this look like? It actually looks like a chain. It actually looks like a chain, right? Because it's a less than equal to. For a set of real numbers, the less than equal to is a chain. And we know chain is distributive. So this is also distributive. The only one which is not distributive is this. Again, because I've eliminated these three options, option D is the right option. But the other way to think about it is, look at this. This is the set here, and this is your divided by, right? Or divides operator. Now, if you notice, what is this? Actually, if I draw the Hess diagram, I'll get 2, 3, and 5, right? I'll get 2, 3, and 5, right? Yeah, I'll get 2, 3, and 5, and all of them divide 30. Okay, so this is what I got. And what is this? This is nothing but your diamond, no? This is the center part of the diamond. This is the whole diamond. And if your lattice is a diamond, sorry, not a diamond, sorry, this is your kite lattice, I'm sorry. Okay, so this is basically your kite lattice. And we have seen that if the Hess diagram is a kite, it's not distributive, right? So this is the final answer. D is not a distributive lattice. Everything else is a distributive lattice. Again, we are simply using the properties that we have studied in the course. Right? And that's one of the fastest ways to solve these problems. If you understand the properties and if you can apply them smartly, you'll get answers very, very quickly, right? So let's go to the next question now. Okay, so what does it say? It says, I have two elements of a group, right? So I have two elements of a group. Order of element A is 17, order of element A is 18, order of element B is 18, right? If A and B commute, which means AB equals to BA, right? So AB equals to BA. We are given that commute basically means AB equals to BA, right? So then what is the order of AB? Let's see, what is the order of AB? Actually, it's very straightforward to answer. I can answer it in one line, but let's work it out slightly, right? So because of this, I can write this as AB power K equals to BA power K, right? I can write this, right? AB power K equals to BA power K, right? And if you notice, look at this, because AB power K equals to, actually, instead of writing it as BA power K, let me actually do this. Okay, so AB power K is what? What is AB power K? AB into AB into AB, so on and so forth. Now, because A and B commute, I can actually move A here and B here, right? Similarly, if I keep doing this, I can get all the A's next to this A, all the B's next to the last B, right? Next to the last B. So I can write this as A power K, B power K by repeatedly applying the commutative property, right? By repeatedly applying the commutative property, I can write it as this, right? And look at this. Now, if AB power K equals to E, we want to find the K, right? See, if AB power K equals to E, then the order of AB equals to K by definition. So we know that AB power K, by just using this commutative rule over and over again, I wrote it as A power K plus B power K equals to E. I already know that A power 17 equals to E. I also know that B power 18 equals to E. right? I already know that. So what should this k now be? This k, look at this, a power k and b power k equals to e, right? Look, important part is, what should this k be? Shouldn't this k be the LCM, or the least common multiple of 17 and 18? Right? And what is the least common multiple of 17 and 18? It is equal to 306, right? So if k equals to the least common multiple of 17 and 18, because 17 and 18 here are co-primes, no? That's why this is more easy to compute, because they're relatively prime to one another. That's what I mean. Okay, so 17 is relative prime to 18 because the GCD equals to 1. So computing their LCM is basically simple multiplication, right? So now what is k? K is nothing but the LCM. So the answer here is 306, because order of AB, right, is nothing but AB power k equals to E, and we discovered that k should be equal to the LCM. So the answer here is 306, which is the LCM of 17 and 18. Very simple point. So now let's go to the 12th question. Okay. So what is the first statement here? Okay, if g square equals to E for all g, then g is abelian. We've actually proved this in the course videos, right? So this is, again, I've written this slightly. We can write g square equals to E as g equals to g square, right? If g equals to g square, right? So we have proven that if g equals to g square, then g is an abelian group. If, again, I've written this also explicitly, if g equals to g square, right, then what is g square? G square is nothing but g into g inverse, which is equal to E, right? So this is something that I've also proven. It's literally 3-4 lines of proof. I've done this in the course videos when I explained the properties of abelian groups. The second one is an interesting one. The second one says every group of order 1, so every group of order less than 5 is abelian. This is slightly tricky. Okay, so let's assume I have a group of order 1. Okay, let's assume the order of the group is 1. Okay, now if the order of the group is 1, okay, then what happens? If the order of the group is 1, then the order of every element in the group, since it should divide the order of the group, right, order of an element A divides order of the group, right, which means order of every element should be equal to 1, right? If every element order, right, if every element order is equal to 1, right, or if every element order is equal to the order of the group, so order of element equals to order of group now. And we have seen that if this is true, then it's a cyclic group, right? And we know if a group is cyclic, it is abelian. Again, this is something that we have stated multiple times in the course videos also, right? So the first case is less than 5, right? Which means I have to do it for 1, 2, 3, and 4, right? If the size of the group is 1, we have proved that it has to be abelian. Okay. What if the size of the group is 2? Can we do something? If the size of the group is 2, then order of elements can either be 1 or 2, because order of element has to divide order of the group, right? If it is 1, everything is good. If it is 2, what happens? If the order of an element equals to 2, then what happens? Let's see, right? If the order of an element equals to 2, then what do we have? We have a square equals to E, right? If order of element equals to 1, right, then we go through this logic that we have seen in the case of order of element equals to 1 here. So we can go through this case, right? If order of the element equals to 2, right, which means a square, there exists an element where a square equals to 2, then order of the element equals to, there exists an element A where the order is equal to the group, right? There exists this element, right? There exists this element. Look at this. If the order of group is 2, then I can have elements of order 1 or elements of order 2, right? If I have elements of order 2 now, right? So, okay, if I have elements of order 2, then order of the element is equal to order of the group, making this abelian, just like in the previous argument, right? Very simple. Now, the third argument here is, if order of group equals to 3, what happens? If order of group equals to 3, then the order of elements can only be 1 and 3. It can't be 2, because the order of element has to divide order of the group, right? It can only be 1 or 3. It can't be 2, because order of element has to divide order of group. So if it is 1, we know, we have seen this argument earlier. If the order of an element equals to 3, what does that mean? Which means there exists an element where order of A equals to order of G, right? Then this is abelian. Right? This is abelian then, just the way we have seen earlier, right? Just the way we have seen earlier. If the order of element equals to order of group, then it is abelian. The fourth case is order of group equals to 4, which means the order of the elements can either be 1, 2, 3, or 4. Sorry, it can't be 3. Sorry, because 3 does not divide 4. So it can either be 1, 2, 4. If it is 1, we know it. If it is 4, then order of the element equals to order of an element equals to order of group, and hence it's abelian. Done. What about square? This is the slightly tricky part, right? This is the slightly tricky part. So there exists an element. So if there exists an element whose order is 2, right? What does it mean? It means a square equals to e. If a square equals to e, what does that mean? It means a equals to a inverse. And we know that if see, we have 3 options, right? That all the elements have order 4 or order 2 or order 1, right? If you have elements of this type, this is abelian to start with, right? So every group, so this is actually a very interesting property which I've not mentioned in the course videos. It's a good property that every group of order less than equal to 5 is always abelian, right? For 5 and above, you can't use this same trick here, right? So this is actually a good good question actually, which is testing your knowledge of properties. So let's look at 13 now. Okay. So let G be a group with order 20 and H be a non-abelian subgroup. Okay, it's a non-abelian subgroup of G. So assuming that H is not equal to G, what is the order of H? Okay, so what are the possible orders of H? Remember, we know that order of H should divide order of the group. We know this, right? We know this, which means because order of the group is 20, what are the possible values? The order of the group can be 1, 2, 4, 5, or 20. 10, sorry, 10 is also there. 10 or 20. Now, right? 1, 2, 4, 5, 10, or 20, right? So 1 is a trivial group, right? So just let's ignore, right? Every group, right? So all these groups. So is that right? So I can have 20, I can have 10 also, right? So okay, so all the groups of orders 1, 2, 4, 5 are abelian, just the way we have seen right now, right? Right now, if because we said H is not equal to G, this is also ruled out. So the only option that is left out is 10, because it says non-abelian, right? It says non-abelian. That's why all these are ruled out, and it says H is not equal to G, so this is ruled out. The only option left is 10. So the answer here is 10, right? And that's because, and the answer here is 10 primarily because of this principle that we have discussed in the concept of abelian groups, sorry, in the concept of subgroups. Okay, sounds good. So this is 13. Okay, we'll try to solve as many problems as we can. Again, some of these problems are very, very simple and straightforward, right? So the question here is, let A be a set of all integers and the binary operation is defined as max. Again, we have seen this in the course videos itself. Is this a group, abelian group, semi-group, monoid, right? Again, we have seen this example, but let me just solve it. Closure. Okay, it is closed. Obviously, max of A comma B will be one of these two, right? And since A and B belong to the set A, obviously, set of all integers, this certainly is closed. What about associativity? Actually, you can also show associativity because you can show that A star B star C equals to A star B star C. Again, we have shown this in the course videos, is equal to max of these 3 elements, A, B, C. So both sides, because max is associative. The max function is associative. Hence, this is associative. The challenge here comes to identity. The challenge here is identity. The identity does not exist to this, as we've discussed in the course videos, because this satisfies closure and associativity. It's a semi-group. If it satisfies identity, it will become a monoid. If it satisfies inverse, it will become a group. If it satisfies commutative, it actually satisfies commutative, by the way. Max of A comma B is max of B comma A, but it's not an abelian group because it's not a group to start with, and it's also not a monoid, right? So this actually satisfies commutativity. So you can think of it as a commutative semi-group, right? Again, we have discussed this in the course videos also. So straightforward question from the course videos. Okay, so this is a slightly interesting question. The number of edges in the hash diagram of this. So if you look at this, if you look at 5, 4, 2, 3, if you look at 5, 4, 3, what are the divisors of 5, 4, 2, 3? If you think about it, I can write 5, 4, 2, 3 as 11 multiplied by 17 multiplied by 29. This is the prime factorization of 5, 4, 2, 3. right? So which means if I have to draw the Hess diagram for this, how would I draw it? 1 certainly, right? 1 will be there. So I'll have 11, 17, and 29, because all three of them will divide 54, 23, right? Similarly, 11 into 17 will also divide. Look at this, 11 into 17 will also divide this, right? Similarly, 17 into 29 will also divide this. Similarly, 11 into 29 will also divide this. Right? Look at this. I'm just using all the possibilities of prime factors. Now, all these three will divide 11 into 17 into 29. Okay, now let's count how many. This is your Hess diagram, right? This is what your Hess diagram looks like. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 edges in this Hess diagram. Right? It's very simple to draw this Hess diagram actually. Right? Of course, the challenge here is to come up with this prime factorization. But the moment you come with this prime factorization, drawing this is straightforward. Right? So now let's go to the next question. Okay, so which of these statements, so consider the following statements. Okay, union of two subgroups is a subgroup, right? So let's see, is union of two subgroups a group? Actually, union of two subgroups, it's not, right? Again, actually, we discussed this in the course videos. We took this group, right? We took the addition modulo group and we said 0, 1 and plus 4 is a group. Similarly, 0, 2 with plus 4 is a group. But the union of both of them, we've discussed this in the course videos, but the union of both of them is not, this is not a union of two subgroups is a subgroup. No, this is a subgroup of Z4. This is a subgroup of Z4, but the union of them is not a subgroup because this is not closed. It's not a group to start with, right? So this is not true, or this is false, right? So one is false. Okay, so let's see. So this is false. Let me write it down. Intersection of two subgroups is always a subgroup. Again, we have studied this. Intersection of two subgroups is always a subgroup. So this is true. If G is a cyclic group, okay, so the third one is if G is a cyclic group, right? So the first one, union is false. Okay, this is true. What is the question here? Which of the following is not true, or which of them is false? Okay. Certainly one is false. Okay, certainly one is false. 2, so this is not true. Okay, because 2, okay, so because they both have this different sign, right? Again, this is slightly confusing. There is not here and there are trues here. Now let's look at the third statement, right? If G is a cyclic group, okay, one second. If G is a cyclic group, every subgroup of G is also cyclic. Actually, this is true. Actually, this is one of the interesting properties of groups. Okay. Actually, I think I forgot to mention this in the course videos. So if G is a cyclic group, then every subgroup of G is also cyclic. Actually, this is true. So what happens now? Which of them is not true? Okay, so what does this first statement say? First statement says 1 and 3 are true. Okay, is this true or not? So 1 is not true. Okay, so this statement is false. Okay, so this statement is false. What about this? Okay, this statement is false, right? And the question is which is not true. So yes, this is the right answer, right? So the second option says 1 and 2 are false. So is 1 false? Yes, 1 is false. 2 is not false. So this statement is also not true. So I think there is a confusion. I think there is some typo in this question. So basically, let's forget about these options. This statement is false. This statement is true. The third statement is also true. Okay, I think there is some mess up here with the not. Okay, I think that's the mess up here, right? So anyway, so let's look at the core statements here. The first statement is false. Second is true. Third is true. Okay, sounds good. So 17th question. Again, I'll try to solve as many as possible. So what is the 17th question? Okay, so it says, okay, let me just scroll up a little. So it says f is a function from B to C. So I have a set B, I have a set C, right? F is a function from this, and G is a function from A to B. Okay, so G is a function from A to B. Now it says f of G. Okay, so f of G. So first I apply G, f of G is a mapping from A to C. Very good. So given that H is an onto, so this function is H. Okay, they're calling this function as H, right? So we are given that this is onto, which means every element here has a pre-image in this. Then which of the following is true? So again, we've actually discussed this in the course videos also. So imagine this. right? Imagine this case. Imagine I have this. Okay, so let's assume I have some 3 elements here. Okay, so so if I have this, now look at this. Now is h function onto for every image, for every value here. Look at this, for every value here, there's a pre-image here, right? So both f and g need not be onto, because g is not onto. There is some value here for which there is no pre-image, right? So g is not onto, but f has to be onto. So which of these options? F should be onto, but G need not be onto. So option B is the right option. Again, we have seen this example in the course videos also. Okay. So now let's go to the next question. Some of these questions are easy, as I told you, right? So consider the cyclic group G of order n. Okay, it's a cyclic group of order n, and let A belong to G. Then which of the following can be a generator of A? Very good. So we have seen this property, right? We have seen this property that generator of, so for any item, for any generator, again, this is a very good one, right? So if you know that A is a generator, so let's assume I have a generator A. Let's assume A is a generator. Okay. Which of the following can be a generator? So let's assume A power R is a generator. Let's assume A power R is a generator. Then we know, we have seen this. If A power R is a generator, then R and N are relatively primes. We have discussed this in the course videos also. Okay, this is a very important property. If you know this property, you can solve this in like 30 seconds. The group has order n, and let's assume A power R is a generator. Then R and N has to be relative primes, right? Now look at this. If I have, so if this is R versus this is R, 2n and n are not relative primes, right? They're not. So this can't be the answer. N square and n are not relative primes because the GCD is not equal to 1, right? So this is also not true. But n plus 1, it is possible that n plus 1 and n are relative primes. That's possible. That's possible, right? That's possible. For example, 18 and 17 are relative primes. So this is possible. So A power n minus 1 is a possible, could be a generator. Okay. So the best option amongst these 4 options is A. Again, for this, you have to know that if A power R is a generator, then R and N are relative primes. This is a very important property that we discussed in the course videos. You just apply it and you get it, right? So if you know that theorem, it's very simple. Otherwise, this is a very hard problem. If you don't know, it's going to be a hard problem. Oh, again, this was a hard problem when I solved it. So let me solve this problem for you. This was hard. Okay, it took me like, I think 10-12 minutes again to solve this. Okay. So if A and B are 2 elements in the group such that it satisfies this, and A cube equals to E, and this is also given for some positive integer n, and E is the identity element, right? Then what is order of B? Okay, so the moment I saw this, I was literally lost. But I said, let's go step by step, right? So let's go step by step. So the first thing is, so let me see. So let me try to understand the properties of AB square. Okay, to solve this again, I had to come to this idea after a lot of thought process, right? So what is AB square? Can I write AB square as, let's see, can I write AB square as AB into A inverse into B? I can write this, right? Because this is equal to E, right? So I can write this as, see, I'm trying to get ABA here. I'm trying to get ABA here. So I can write this as ABA, right? A inverse into B, right? I can write this as A inverse into B. Because associativity always works, right? So I can write this way. So A into A inverse into B. Yes, I can write it this way. This is cool. Now what is ABA? ABA is BA square B, right? So I can write this as BA square B into A inverse into B. Okay. So now what is this? So I'm also given that, see, look at this. What does this mean? If A cube is equals to A, then what is A inverse? A inverse is equals to A square, right? Look at this. If I multiply A square with A, then I get A cube. A cube equals to E, which implies A inverse is A square. Okay, this is a very important thing that we'll keep reusing. That's why I just thought I'll mention this. So where are we? We got we substituted this. We got B A square B equals, and multiplied by A inverse B. Okay. So can I write this as B A square? I'll write this as B A square multiplied by B A inverse B. Okay, I can always write this, right? So this A square, I'll replace with this A inverse. I'll replace with A square, right? I can do that, right? Because A inverse equals to A square. So I've just done that. Okay, so what do I have now? I have okay, ba square into 1 second, ba square into ba square b. Okay, so what is ba square b now? So ba square b is aba. See, I'm trying to use this somehow. I got this, which means I'm going to use aba now. So I have aba. What is this? I know that this is a cube. I know a cube equals to e. So this is now b square a. Look at this. AB square equals to B square A. This is what I wanted to prove. Now, what does that mean? It means A and B square are commutative. They both commute, right? So they both commute, right? So they both, so let me write that. Okay, this is a first result that is very important for us. A and B square commute, which means AB square equals to B square A. This is the first result for us. Okay. The second thing is, now I'll try to see. Now let's write this down. So we have AB square equals to B square A. The first result that we just got, right? Now if I write AB square A inverse on both sides if I multiply, post multiply with A inverse, I get B square. Very good. So I got A inverse here. A inverse and A will cancel out. Okay, got it. Okay. So this again, A inverse, I can write it as A square equals to B square. I can write it like this, right? Because look at this, because this implies that A inverse equals to A square. I just use that. Now, if I repeatedly keep applying this, I can write this as A into B power 2n into A square equals to B power 2n. If I keep, again, this is one application, right? If I keep repeating that, look at this. I again have AB square, right? Again, I have AB square. I'll just say AB square equals to B square A. I'll keep doing it. If I keep repeating this exercise, right, I will get, so by repetition, if I keep repeating this, I can write this for some n. Okay, I can write this for some n. Okay, now let's see. Now I'll try to simplify this further, right? So we know, so again, why did I write it in this form? Because I'm given this and I want to use this. B power 2n minus 1 equals to E. What does that imply? That implies B power 2n equals to B, right? That implies B power 2n equals to B. So this becomes ABA square equals to B. This is what I got. Right now, what does this imply? If I now multiply both sides, what is A square? A square is A inverse. Again, I have this A square equals to A inverse. Now, if I multiply both sides by A, what happens? I get AB equals to BA. Okay, so what is the first result? The first result was A and B square are commute. They're commutative. Similarly, A and B also commute. They're also commutative. Okay, now I'll use all of these things, right? Now let's see, right? So we are given this. Now we are given this. Okay, so this is a powerful result now. A and B commuting is a very powerful result. So ABA equals to BA square B. This is given to us, right? So I'll write AB as BA, right? I can write this as BA. So this will become BA square equals to BA square B. Look at this. This is a very surprising result, right? Look at this. I got BA square equals to BA square into B, which means I got BA square into E equals to BA square B. And I can do left cancellation, which means B is equal to E. If B equals to E, what is the order of the element? Obviously 1, because order of the identity element equals to 1. So the challenge here was, first I had to prove that AB square are commutative. Then using that, I proved that A and B are commutative. The moment I proved that A and B are commutative, everything fell in place. To find out what B is, and this left cancellation is a very, very important idea, right? Because inverses exist. This left cancellation is possible in a group because inverses exist, right? So the order of this element, so because the element itself, because B is equal to E, the order of identity element is 1. Okay, so this was a hard problem, to be honest with you. This was a hard problem, and I actually struggled to solve this problem. It took me quite some time. I think maybe 10 to 12 minutes. Again, it took me some time to figure out that first I had to prove this, then I had to prove this. So this problem is certainly above the gate level, to be honest with you, right? So now let's look at the 20th question. Okay, so let's see what this is. So you have the set Z, okay, and these are complex numbers. This C basically represents complex numbers, right? And Z power n equals to 1 for some positive integer n. So that's your set. Okay, it's a set which consists of complex numbers such that their exponent equals to 1. and the operator is multiplication. Okay, is G a group of finite order? Okay, let's see. See, what does this mean? Look at this. If n equals to 1, if n equals to 1, right? Then what do we get? You get z equals to 1, right? Because 1 power 1 is 1. Very good. If n equals to 2, what do I get? Okay, you get z power 2 equals to 1. What does that mean? And z are complex numbers, right? These are square roots of unity, right? Then z are, so z equals to square root of 1, right? Square root of 1, right? Square roots of unity, right? And okay, so these are square roots of unity. When n equals to 3, what do you have? You have z cube equals to 1. So z is cube roots of unity, so on and so forth. So this set consists of many, many elements. This is not necessarily a finite ordered set, right? Because there are some, again, this is not real numbers. If it were real numbers, everything is good. This is not just real numbers, right? This is all complex numbers. There are complex cube roots of unity, right? Similarly, there are complex fifth roots of unity, right? So it's not a group of finite order. So certainly A is not right. Okay, what about the second concept? It's a group of infinite order. Very good. Where every element has a finite order. Yes, that's true. Makes sense, right? Because how are we defining the elements? See, every element Z here. See, what is the, first of all, before we go there, what is the identity here? The identity, because it's a multiplication operation, the identity is 1. And for every element, there exists an n, which is a positive integer. Look at this. There exists an integer n. There exists a finite number n, finite positive integer n, such that this is equal to 1. Which means every element now Z, which belongs to this, has a finite order, because n is a finite positive integer. So this statement is true. Okay, so B is the right statement here, right? So answer B is the right answer here. Okay, so now let's go to the next question. Again, this is a straightforward, simple question. Okay, so let's go to the next question here. Okay, so what do we have? Let H1 and H2 be distinct subgroups of a finite group, each of order 2. So order of H1, so order of H1 equals to 2, and order of H2 is also equal to 2. Okay, let H be the smallest subgroup consisting of both H1 and H2. Okay, so see, look at this. If H1 contains only 2 elements, what does that mean? See, it has to contain identity. Let's assume it contains another element X. So let's assume H2 has to contain the identity. Let's assume it contains X. Then we want to construct the smallest subgroup that has H1 and H2. So let's try to construct a group which consists of E, X, and Y. Okay. Now the problem here is E is okay because E into X is X, E into Y is Y. What about X into Y? What about X into Y? X into Y may not even belong to this set. That's why we said union of two groups need not be a group. Right? We saw this example, right? So what if, so this may not be a group. This may not be a group. So what if I have E, X, Y again? Yeah. So again, so what if I have X into Y also? What if I have X into Y also? Look at this. X is self-inverse. Y is also self-inverse. Right? X is self-inverse and Y is self-inverse here. Right? Now, what if I have X into Y also? Okay. Now, this group has 4 elements. This group has 4 elements. It is closed. And you can check all the other properties of group also. It satisfies all the other properties of group. So the smallest group that you can construct has size 4. Right? It cannot have size 3. Because if you have size 3, this problem, X star Y, it doesn't exist in the group to start with. Right? And X star Y is not equal to E. Right? Look at this. X star Y is not equal to E. Because X is self-inverse and Y is also self-inverse. If they're not self-inverses, these 2 elements cannot belong to a group to start with. Right? That's why X into Y will not belong here. So you cannot have, it's not that you can have in some cases. No, you cannot have a group like this. This will not be a group. It will not be closed to start with. So the only group, so the smallest group that you can construct has 4 elements. Right? So this is one nice example. Okay, so let's go to the next question now. Okay, so let's go to the next question now. So what does it say? It says, okay, let G be a finite group of even order. Okay, then which of the following statements is correct? So G has, so order of the group is even. Okay, the order of the group is even. The number of elements of order 2 is even. The number of elements of order 2 is odd. There is no subgroup of order 2 and none of the above. Let's see. Look at this. This G will contain, so this G will contain, the identity element. Identity elements order. Identity elements order is 1. So order of the identity element is equal to 1. Right? So this is anyway odd. This is anyway odd, right? So one element you remove. So now this will be odd. Look at this. You remove this element, it will be odd, right? So order 2 is what we care about, right? Now let's assume X is an order 2 element. Okay, let's assume X is an order 2 element. Let's assume X is an order 2 element. What does that mean? Which means X square equals to E, or in other words, X inverse equals to X. It's a self-inverse. It's a self-inverse, right? See, I have odd number of elements here. Look at this. I have odd number of elements here, right? Now, if X is a self-inverse, right? See, look at all of them. Look at all of them. See, G minus E is odd, right? So for all the elements whose order is not equal to 2, see, order can be equal to 1. Okay, order can be equal to 1. That's only set E. Order can be equal to 2. So if order is 3 or 4 or any of them, right? For every element, its inverse also should exist. See, if I have an element X whose order is 3, its inverse is not itself. See, for this, this inverse is itself. For this inverse is something else. So for every element, since inverse exists in a group, they all come in pairs. They all come in pairs. If this element exists, its inverse also should exist, right? So number of elements that are of order 3, order 4, order 5, so on and so forth, they're all even. That's because for every element, since it's not a self-inverse, the element along with its inverse need to be part of the group, right? So if this has to be inverse, see, look at this. This is odd. This is just one number. Now, what can this be? What can this be? This can be odd. This has to be odd. This has to be odd because odd plus 1 is even. Even plus even is even. Now, we have said that the group has even order. The group has even order. One element is already taken out, right? Because of identity. All these elements, the number of elements here has to be even. Okay. If this is 1, this is even plus 1 plus an odd number, right? Is even, which means the number of elements of order 2 has to be odd. Again, this is one way to argue about it, right? Obviously, I can again, none of the above is also here, so I can't solve this problem with an example, right? This is the rigorous way or the formal way of arguing about it. Because I can't solve this problem with an example. Initially, I was thinking I'll solve this example using this, right? Because this is a group of even order, right? I thought I'll show which all elements, which all elements have odd order and even order. But then there's a problem of none of the above. That's why we have to prove it more formally. Okay, sounds good. So let's go to the 23rd question. Okay, so let's try to tackle this. Okay, so let's start with this. Again, this is actually a non-trivial question, but an interesting one. Okay, so I have x power 5 y cube equals to this equals to e. Okay, let's start with this, right? So I have x power 5 y power 3 equals to x power 8 y power 5. And it's a group. E is an identity, which means inverses exist, right? If I multiply both sides with x power minus 5, right? If I pre-multiply with x power minus 5 and post-multiply with x power minus y power minus 3, then what am I left with, right? Then I'm left with x power 3 y square, right? I'm pre-multiplying both sides with x power minus 5, and this is equal to e, right? So this whole thing becomes e, this whole thing becomes e, and this thing, basically think of it like cancellation, left cancellation and right cancellation, because that's valid in a group, right? Because inverses exist. So from this I can say that so from this I can say that x cube y square equals to e. Okay, so this is one thing that I have. I also have the fact that x power 5, look at this, I have x power 5 y cube is also equal to e. Okay, now if I take these two statements now, x cube y square equals to x power 5 y cube. Again, multiplying both sides by x power minus 3 and y power minus 2. So basically cancellation. I'm left with x square y equals to e. Okay, so this is what I'm left with now, right? X square y, right? This is what Is this right? Yeah. I'm left with x square y equals to e, which is also equals to, 1 second, x cube. So if x square y equals to e, then what is x cube y square equals to x square y into x into y, right? Can I write it this way? Yeah. I can write it this way, right? So look at this. Because I have this also, I can write x square y. See, I can write x, because x square y equals to e, I can write x cube y square. See, x cube y square, I can write it as x into x square, y into y. Associativity. And this is equal to e. See, this is equal to e, right? This is equal to e. So this is equal to x into y. Okay, so what did I get here? What did I get to? 1 second. Where did I come here? X square y. I have x square y, and I'm trying to get, what am I trying to get here? I'm trying to get x cube y here somehow. See, I want to see what we're given here is x equals to e and y equals to e. I'm trying to prove that x can be equal to e. So I'm just trying to prove that. Actually, x actually is equal to e. I'm just trying to prove that slightly carefully. So let me erase this. So let's take a step back and try to solve this, right? I have, okay, we got e equals to x square y, okay, which is equal to, what is x square y, which is equal to, can I write this as x cube y? Can I write this as x cube y? How can I write this as x? If I can write this as x cube y, I've solved. Now, how can I write this as x cube y? See, x square y is here. What is x cube y? Just give me a sec. I'm trying to figure this out. This shouldn't be tricky because I solved this earlier in the day. So we got e equals to x. So we got e equals to x cube y square. That's good, right? So x cube y square equals to x power 5 y cube equals to e. Very good. So from this we got e equals to x square y. So these two cancelled out. We got x square, we got y. Good, right? So we get this. Now if I can prove that this is equal to this, if I can prove x square y, right? If I can prove that x square y is equal to x cube y, then I can prove that x equals to e, right? So I'm trying to prove whether x equals to e or not. So just give me a sec. Let me see how I can do it, right? So I have x power 5 y cube equals to e, right? And what all statements do I have? Let's write it down. X power 8 y power 5 is also equal to e, and x cube y square is also equal to e. These are the three statements that I have, right? Now let's see. Now I want to prove that, okay, I also have x square, sorry, I also have x square y equals to e, right? I also have this. Now from these two I can write x cube, okay, x power 5 y cube. I got this. Now from these two I can get this. Now what I want to get is x cube y equals to x square y. Okay, so this is what I'm trying to achieve at. So just give me a sec. Let me see. E equals to x square y. Can I get e equals to x cube y also somehow? So where are we? X power 5 y square. So we got these four terms, right? So we got x square y. So if I multiply both sides with y, I'll get y. This is not working out. I think I'm stuck here a little. I solved this. I thought this was straightforward to solve when I solved it earlier. Again, it's very, very common to get stuck on problems like this. Very, very common, right? And because there will be one small hint that we tend to forget, or we tend to overlook, and then you're stuck. That's what happens a lot in some of these proofs. So e equals to x square y equals to x cube y. So I want to prove this. I still don't have this. If I have this, I know that x equals to e. So I want to prove this. How do I prove this now? Okay, let me see. Okay, sorry, I'll skip this because I'm also slightly exhausted. I think I'm not thinking clearly. So I'll skip this. We'll anyway provide the solution with the test questions itself. I think I messed it up somewhere. Just give me a couple of minutes. Let me think about it, If I can crack it, great. Or else, I'm sure we anyway write detailed solutions to all the problems. We have probably a couple of more problems, but I seem to be stuck here. So I have E here. X cube y square equals to x power 5. Okay, so what? Okay, let me go back to step 0, right? So E equals to x square y. Okay. So I need to prove. Now that x cube y. So I need to prove x cube y is equal to E. Let me try to do that. How can I get x cube? How can I get x cube y term? With this I can't get. So with this I'll get only xy term, right? With this I'll get xy term. So let's see. Again, I'm getting, so if I resolve these two, what do I get? I get x into y is also equal to E. If I resolve these two, if I cancel these two terms, if I equate both of them, I get xy equals to E. Right? If I get xy equals to E, which means y is the inverse of x. Right? It means y is the inverse of x. Right? This is what I'm getting. So I got xy. Oh, so I got it. I think I got it. No. X square y equals to E. So if I multiply it with xy, right? If I multiply x square y with no, I'm still not reaching here. I'm struggling to see how I can get x cube y equals to E. So I got x square y equals to E. This is good. This was straightforward. Now I somehow have to get x cube y equals to E. I'm still thinking which equation am I which equation am I overlooking here? So if you look at these two, okay, if I use these two equations, what do I get? I get x square y equals to E. From these two equations, I get this, and I get xy equals to E. So if I use both of these now, I get x cube y square. Again, I get x cube y square. I'm getting this now again. No, I don't want any of these. I want to get to x cube y equals to E. How do I do that? So I got xy equals to E. I'm still thinking. Just give me a sec. Okay, if I can't solve it, that's perfectly okay. We anyway have the detailed solution in the. Anyway, let's okay. Instead of just taking more of your time, let's anyway solve this. Anyway, the solution is available in the online test that you have taken. There will be a detailed solution which solves this carefully. And if there's any question, do let us know. I'll also sit down and figure out. I think I'm slightly getting saturated with my thought process. I'm missing something here. I'll have to sit down and think carefully. Not in a live session. Okay. So we have two more questions. Again, most of these questions are straightforward. I'm very happy that we have done at least. Actually, this is straightforward, right? Actually, this question we actually discussed in the course videos also, right? So we saw that a totally ordered set is going to be Boolean algebra. We define what a Boolean algebra is only when n equals to 2, right? For any, so we've already seen this, right? If a totally ordered set, again, this is something that we discussed as an example for Boolean algebra, right? So if I have a totally ordered set or a chain, if the chain length is more than 2, it's not a Boolean algebra, right? But this is a Boolean algebra, right? So this is straightforward from one of the theorems that we learned. Similarly, this is also a straightforward problem actually. So this problem is also straightforward because if R1 and R2 are transitive, then R1 union R2 is also transitive. This is not true, right? Because imagine if I have, let's say, R1 union R2, right? So imagine if I have 1, 2, right? Imagine if I have 1, 2 in your R1, right? Let's assume R1 consists of only this relation. Let's assume R2 consists of only this relation, let's say, right? Then the union of both of them, R1 union R2, consists of both these relations, 1, 2 and 2, 1. Remember that these two are transitive. These two are transitive. R1 and R2 are transitive. But this union is not transitive because 1, 1 doesn't belong to the union, does not belong to R1 union R2. So the union, so if you have two transitive relations, the union need not be transitive. So this is false. What is the next one? Number of relations on a set of n elements that are both symmetric and anti-symmetric. Okay, remember, this is a very interesting question, right? All symmetric matrices are anti-symmetric. Okay, if you notice, all symmetric matrices are also anti-symmetric. And we have shown for anti-symmetric matrices, we have shown that the number of elements is 3 power n choose 2. Again, we have 3 because we can either connect So again, we've discussed this in the course videos, right? I'll not again derive it here in the interest of time. So in the course videos, we've anyway derived this. So this is certainly true. The only catch here is that every symmetric matrix is also anti-symmetric, and we know the number of anti-symmetric matrices is 3 power n choose 2, right? So first is false, second is true. So option B is the right option here. So these are the easy problems. I'm still thinking on the problem that I got stuck in. Right? I'm still thinking of this problem. Where did I get stuck? So anyway, the answer for this is, I remember solving this. The answer for this is A. Anyway, the detailed solution will be given in text form. I'm sorry, I got stuck here. I should have written the notes properly. I've not written the notes for this question. I just thought, okay, I only write notes for harder questions. For the simpler questions, I'm like, let's go solve it. I think something very simple is what I'm missing. Anyway, no problem. And yeah, you'll have detailed written solution in the course video. In the online platform when you submit your questions, right? So very importantly here, for most of group theory, I strongly recommend that you write a two-page summary. Okay, I strongly recommend that you write a two-page summary of all the theorems and of all the statements, right? And all the properties, all the theorems, statements, and properties. I strongly recommend you write all of them very concisely. Try to write it very concisely, because this will help you revise concepts. Okay, there's so many properties, there's so many theorems. Don't try to prove them in the examination setting. It's very hard. For example, proving that order of a subgroup divides order of a group, the Lagrange theorem. This is hard in an examination setting. So, but knowing this property can help you solve many problems very quickly, right? So I strongly recommend, especially for sets, relations, functions, groups, and lattices, I strongly recommend that you write a two-page summary very concisely, using all the shortcut notation that I've also discussed in the course videos, and try to keep revising this regularly so that you know what's happening.